Okay, so the math dealer here, and today I am going to knock out some of those questions from that Honors Calc Summer packet. I know, right? Too much fun. This is just a little bit of a brain charge for you guys. Okay, so the first question that was asked for me to do was find the vertex. Okay, so it's always nice when the equation of the quadratic is sitting in this form. I know, right? You're like, yeah, I love it when it's in that form. However, it's not always in that form because if it was, it's just h and k. Sometimes we have it in the form of ax squared plus bx plus c. All right, so if that's the case, I just do my little negative b over 2a. Oh, I should probably write that equation down. Sorry about that. All right, so when you're trying to find the h, you're going to use negative b over 2a. All righty, so I'm going to take my negative 8 over 2 times negative 2. So I get negative 8 over negative 4, which we all know and love to be 2. But you are not done yet because remember, a vertex is a point, right? So my h is 2. I got that. Now I'm going to plug it in and figure out what my k is. So, of course, I plug it in negative 2 times 4 plus 8 times 2 minus 7 because I squared the 2. That's where the 4 came from. So when I do this little work, I get k is equal to 1. Domain of a quadratic is always all reals. The range, however, since this particular parabola is opening down, the range goes from negative infinity up to negative 7. Okay. Now, we first to graph these things, I suck at graphing. I'm not the best grapher in the whole wide world. But anyway, that's okay. So I plot my vertex at 2, 0. I also always like to get like another point. To me, the y-intercept is always golden, if at all possible. Plug the 0 in and I get the y-intercept to be negative 7. Now, very fun fact about these, I have an axis of symmetry, right? Quadratics always have an axis of symmetry. So what I can do is just mirror it over. So if I went 2 units to the left, I can go 2 units to the right. I know it's all coming back to you, isn't it? You're like, oh, I do remember all that kind of stuff. So there's my parabola. And yes, if I could draw, it would connect the dots, la, la, la. But, whoever had me in class knows not the best drawer in the world. Okay. So now we're going to come over here. The next question was asked for number 9. These are just some factoring to solve. This one might have thrown a few people because you got to factor by grouping. So I'm going to factor out my x cubed, and I'm left with 5x plus 2. But on these last two, I'm going to factor out actually a negative x, and I'm left with, again, 5x plus 2. It took me a minute to think about that. All right, so now I say, okay, well, that's cool. I have a 5x plus 2 in both of those quantities. So I'm left with x cubed minus x. And you're probably saying to yourself, hey, self, can I factor that? Of course you can. Factor out the x. And you really should factor out the x so you don't lose your 0. Right? So now we set each of these equal to 0. And I get x equal to 0, x equal to negative 2/5. And of course, x equal to plus or minus 1 because that's x squared minus 1. Could you factor that? Of course you could factor that. But once you get to the difference of 2 squares, sometimes it's just as easy just to get those values. All right, the next question that was talked about was domain. Remember, when you're dealing with square roots, domain is always the radicand has to be, when you deal with square roots, the radicand has to be greater than or equal to 0. If it was an odd root, like a cube root, a fifth root, it's all real numbers, no big deal. But if it's an even root, that radicand must be greater than or equal to 0. And then you just solve. I'm going to slide my 7 to the other side. And don't forget, divide by a negative. Bells are ringing. People are screaming, flipping inequality. So I end up getting negative infinity up to 7. And yeah, I can include the 7, so I can use brackets. I know, right? Fun. Because you can take the square root of 0. This next question deals with denominators, right? We have a rational function. So we really have to figure out, hey, when does this denominator equal to 0? Because whenever it's equal to 0, the rational function wouldn't exist, right? It's either going to be a whole or a vertical asymptote. So I factor out the x squared. I'm left with x plus 3. Over here, it's just like we did earlier, right? Factor out the 9. I'm left with x plus 3. So I get x plus 3 and then x squared plus 9. Remember, we do not want that to be 0. Okay, well, that means x cannot be negative 3. And could I write that in interval notation? Of course I can. By the way, x squared plus 9 is never 0 because you can't square a number, add something, add a positive number to it, and get 0. At least not in the real number system. All right, this guy here, logs. Remember just the log-an, also known as the argument, but you know I do love a good log-an. That has to be greater than -4. In this case, it cannot be 0. What am I getting at? You can't take the log of 0. It has to be positive and has to be greater than 0. And then likewise here, right? X would have to be greater than 0. Um, and of course, usually we write everything in interval notation. All right. With that being said, I think the composition functions you guys were good with. If not, I think I have plenty of videos on that as well. All right. The last two problems that were asked of me were these 29 and 30, right? Deals with some logarithms. I know it's been a while. So one pattern I want you to think about is b to the box is equal to triangle. That pattern gets rewritten as the log of triangle base b. Okay, so let's not forget that. I'm going to use that property when I sit down and solve an exponential. Because to solve an exponential, I have to rewrite it as a logarithm. So here we go. I'm going to subtract 15 from both sides. I probably should have a calculator here, but you know me. Sometimes I don't always put the calculators out. But you know where we're going with this, right? I'm subtracting 15 from both sides. So I end up getting 2,500. And I want to say it's 86. Check my work, you know how I. And so then I'm going to divide both sides by 6. And when I divide by 6, I should get 431, I think. Yeah, 431. And then now I do my little rewrite. So I take the power, right? And I do the log of the 431 with the same base. And that's kind of the key here. Remember, the base of the exponential will also be the base of the log. So now I'm just going to kick this out on a calculator. Remind you, to solve using the change, to evaluate using the change of base theorem, I take the log of the argument divided by the log of the base on my calculator. Don't forget to use parentheses because sometimes it won't read that. So I end up getting 2.917. I'll just stop it at 2. I'm going to add 2 to both sides, and it's not like you can't solve from here, right? I know. You're like, yeah, I got you. I got you, math dealer. So -4.917, done. Call it a day. This one over here is going to use a property of logarithms. So I say, well, the log of A minus the log of B can be written as the log of A over B. If these are properties you don't really remember, I do have some videos on my YouTube channel called Cutting Through Logs. I know, right? How fun is that? Cutting through logs. Get it? I know. I crack myself up. All right, hurry up. So here we go. So I have the log. I have the log of x over x minus 1 is equal to 1/2. And the base of this is 4. Mind you, you can only use these properties when the bases are the same. So I take the base, raise it to a power, equals the log-an, also known as the argument. 4 to the 1/2 power is actually just the square root of 4. So I get 2x over x minus 1. I know I'm going fast, but like I said, we're reviewing for honors calc, so I know you guys have quite a bit of math knowledge. And I end up getting x equal to 2. Should always check your work. Make sure you don't zero any of these guys out because you cannot take the log of a 0. All right, don't forget